webinar. How does that look? Perfect. Thank you, Carolyn. All right. Welcome, everybody. Thanks for joining us this evening. And I think I have to reshare screen, so give me just a moment. Actually, let me make sure I'm sharing for, there we go. So sorry, folks, I'm getting a little bit of an odd view here, so I just want to make sure I'm sharing the right thing. Thank you for your patience. I don't see my slides. Are you all able to see my slides? Yeah, no, okay. This is always fun. Thank you for your patience with this. Let me find my slides again. My window with them has gone away. This is always fun, technology. All right, thank you for your patience, everybody. I had to open up a new window. I think I got it, Carolyn, thank you. We'll try one more time. And of course, you know, in a 45-minute presentation, it's always great to be fumbling. All right, how about now? It's always also weird not being able to hear folks. Okay, perfect. Thank you for that. I am so sorry for the hiccup. This is a new platform for all of us, and even though we practice it, of course, there's a little bit of a snafu, but I'm excited to welcome you all tonight to think about the next generation science standards and how they really are transforming what our classrooms look like in terms of science teaching and learning. And so I will just preface that I know this program this evening is inclusive of a lot of ages, and I'll primarily be talking about kindergarten through third grade. So I want to make sure that you're aware of that, and hopefully we're in the right spot. And one of the things we're hopefully going to explore today is how NGSS, the Next Generation Science Standards, have changed classrooms. And we'll get a chance to do a quick introduction and overview, and then we'll focus on the shifts at the heart of the standards and how practices emerge in classrooms that support student sense making in science and what this type of learning looks like in our classrooms. So starting with introductions and overview, I am Jill Grace. I direct a project called the K-12 Alliance, which is a science and engineering project at West Ed. And the K-12 Alliance has existed for well over 30 years, primarily working in California, advancing science education. And I just want to express my gratitude tonight that my colleague Andrea is joining us. She actually was a kinder teacher for a number of years, and she's going to be providing support in the chat tonight as well as the Q&A. And you might hear her pop off mute a little bit to support me if we need it as we move forward. We weren't really sure how many people were going to pop in and how I was going to be able to navigate this fascinating Zoom platform along with the chat. I wanted to give a little context with K-12 Alliance in case you aren't terribly familiar with us. And really our work focuses on innovating science education in ways that transform teaching and leadership, and really to help empower all of our students. And I would love to tell you this is for college and career readiness, and I'm wholly convinced that kids that learn this way will lean in that direction. But personally, I'm much more interested in having our students emerge through our school system in expanding their curiosity about science and engineering, and more so they can become folks in society that actually don't lose that as they get older, right? And so learning in this way, I think you'll see, we hopefully inspire more kids to consider science and engineering in college and career. But we really just want them to be very excited about science in general as well, which is pretty exciting. So we are curious about you and getting to know you all just a little bit and thinking about what perhaps sparks science curiosity for you. And so what we want you to think about is perhaps what sparked that curiosity in science as a child, or what's currently sparking your curiosity today. And if that's a little hard to think about, you can even think about a young child in your life and think about what sparks their curiosity. And I'm offering a series of images for you, and you'll be able to see them larger in just a moment, to see, does any of these resonate with you in terms of what might spark your curiosity? And we're going to be chatting a link to a Padlet that has these images, and ask you to hop onto the Padlet for a moment and find an image that best matches what you think sparks science curiosity of yourself or somebody else that you know. And if you're so inclined, also feel free in the comment to introduce yourself. So find the one that resonates with you, or you can upload your own. And in the comment, just introduce yourself. So, hi, I'm Jill. I'm a science teacher in Long Beach, and explain why you chose that image as one that represents what sparks your science curiosity. And we encourage you to interact with the posts of others. So you can do this by leaving comments or leaving a heart reaction. And if you have not used Padlet before, on the screen, there is the plus icon that you can use if you'd like to upload your own image. And to leave a comment, you just simply start typing in the comment box. And if you'd like to react, you can click on the heart. And so we're curious about you and what sparks your curiosity. And I'll see if I can pop out. I think I lost it. So I'm gonna have to pop in here, and I'd like to bring this up so we can look at it together. And if it's really confusing to open up another window, feel free to just type in the chat if any of these images might connect to a way that sparks curiosity for you. And so I can say that for myself as a young child, a few of these would have, but the rocket probably would have for me, because I'm the generation where we had the opportunity to watch all the space shuttle launches, and I really wanted to be an astronaut for a really long time. So we have a couple of you commenting. Yeah, I love the learning and growing from eating where you grow. One of my colleagues actually grew up on a farm, and that was her stories of what sparked science curiosity for her, which I loved. All right, so I'm looking at our participant number. We'll give you another moment to play around on the Padlet. And thanks for the comments in the chat as well. So we hope some of these made you at least smile a little bit. For a lot of us, we all have different reasons of what might pique our interest in science. And so it's kind of a fun thing to explore. And we'll keep that Padlet up. So if that's something you'd like to return to and think about, we invite you to do so. So thanks for taking a moment to help us get to know you a little bit better. So we do want to leverage the idea of curiosity tonight, and the idea that curiosity about the world around us is really everywhere, and it is actually at the heart of science. And here we have some first graders that are exploring a really unusual instrument in their classroom, and it's creating a lot of questions that they have about what's going on with this instrument and what's happening. And it really speaks to this idea that all of our kids are natural scientists. We are all naturally curious, and how exciting that we actually finally have a vision in our science standards, that holds that at its core. I can't say that that's always been the case, but it certainly is true today and certainly true with these current science standards. And so by supporting students in their curiosity and helping them make sense of our world, I often call that sense making. So you'll hear me say that quite a lot this evening. They are scientists in our classrooms and in our communities. And so tonight we actually are going to lean into these first graders and go on a sound adventure with first graders to help us understand a little bit about how our classrooms today are changing. And so we're going to start by thinking about the shifts at the heart of the science standards and think about how this gets us to curiosity. And it's actually been a decades-long journey. I'm happy to tell you, this isn't something that's new. It's been brewing for quite a while. And it involves synthesizing a large body of research about how people best learn. And so a year after our last set of science standards were released, this pivotal publication came out, which synthesizes decades of research and really illuminated some key themes that are really important to attend to support deep learning of something. Shortly after that, I guess not shortly, but in 2007, another really important consensus study was released called Taking Science to School. And these two publications probably are the most pivotal ones that influenced the publication of framework for K-12 science education. And all of these are, I'm going to say the word consensus studies, which means everybody involved in producing this had to agree with what went on the paper in terms of how they interpreted the research and interpreted the vision. And they came from the National Academy of Sciences. And this really provides the theoretical underpinning of the next generation science standards. And this is the symbol that we often see for that. I also want to lean into a colleague, a good friend, a science educator, a language educator, Dr. Oki Lee from New York University, who actually calls a framework for science education a love letter to our youth, because it really is the vision of recognizing that all of our students bring such beauty and assets to our classrooms, and how can we actually have a science program that leans into that and supports that. So this has led to a fundamental shift in what happens in our classrooms. And that shift is a shift from learning about science ideas to one where students are figuring out and explaining phenomena and problems. So I'll spend a bit of time unpacking that, and then we'll get a chance to kind of peek in to a classroom and see what happens. So in terms of what this means, the standards are what they are, but they don't actually tell educators how to go about doing this. And so a couple of years after the standards came out, there started to be like calls of action for instructional material providers, for folks that were designing curriculum to really think about what is the vision of this and how should it play out in instruction. And these innovations were one of the things that was identified. And at the heart of this is having the students in our classroom make sense of phenomena and design solution to problems. And the other novel innovation of this is something called three-dimensional learning. So I'll spend more time tonight unpacking those two, but it's those two in concert with each other. And this notion that the standards are written to align to English language arts and mathematics and build a progression from kindergarten all the way to 12th grade. So given my audience tonight, I'm going to pause here right now to say that those primary students, those primary standards are so critical to provide an important foundation for our students as they move forward. And we do see big differences in students in upper elementary, middle school, high school who are lacking that foundation. So it is very much a fundamental human right of all of our students to have access to this in the primary grades and in all grades. So I do want to mark that. When we attend to all of this, then we start to reach that vision of all standards, all students, which is really important because it is the right of all students to be able to have this. It shouldn't just be some kids who end up having that teacher that get to have science that year. It should be happening in every classroom. So The other thing that's really important to remember about this whole notion of having students make sense of phenomena and design solutions to problem is that whole sparking curiosity thing we talked about. This makes the science really relevant and meaningful for students and positions students in our classrooms to be coming to understand ideas in the same way that scientists and engineers understand. So you might hear me say mirror how scientists do this or approximate how scientists do this. And that's what I mean by that. So, and this has been called out a lot in the literature, right? So the work that scientists do reflects who they are, what they care about, and how they experience the world. And it should be no different for our students. So the big question is, how do we make that happen in classrooms? So I'm going to start by sharing with you an example from, or a couple of examples from our early implementation initiative. This was a 6-year grant that we had right after the standards were adopted in California, involving 8 districts and 2 charters. And I'm going to give a shout out to philanthropic funding because this program was funded by the Bechtel Foundation and the Hastings-Quillins Fund, and allowed us to have this rich, I'm going to call it a playground for 6 years, where we had these amazing teachers help us figure out, what does this look like in instruction? What is phenomena and how does it play out? How do we help students really come to develop these more sophisticated scientific ideas from these interactions that they're having? And so it was really a gift to work with these teachers for 6 years. And one of the products of the early implementation initiative was actually producing units that was driven by the teachers wanting to share what they had learned. And so these are some examples of explaining phenomena and solving problems in our K-3 units. So we have kinder students really kind of exploring a lot of like what Leslie and John talked about earlier. So some objects move, some don't. And in this case, really just understanding what causes movement and what doesn't cause movement. Rolling can totally be a part of that, right? Our first graders actually were exploring, wow, these fire trucks, they have these really loud sounds that they are using to communicate. And first graders, this one makes me smile because the origin of this was actually the Great Chocolate Disaster, where, you know, I left chocolate in the car and it totally changed. It eventually morphed into the crayons have changed. But, you know, what happens when things change, when we don't expect that? And our third graders actually look at objects moving in different ways on the playground in these particular units. So hopefully this gives you a little bit of a flavor of what I'm talking about when I mention phenomena and solving problems. And I'll mention that the third graders actually work to ultimately design a playground that meets a challenge that they are presented with. So to approximate the work of scientists and engineers, phenomena and solving problems help us get there. And that, like I mentioned, is where we can spark that curiosity. And as they work, students work in 3 ways to be able to explain phenomena or solve problems. And just like scientists do. So scientists and engineers engage in practices to do their work. And they work with ideas that cut across disciplines. So you heard Leslie earlier talk about patterns that do that, and that is true for science as in other areas. And scientists and engineers generate knowledge and solve problems. And so we want to offer opportunities in our classrooms where our students are doing these same things. Looking at it a little bit differently, I'm just going to judge these things together. These 3 dimensions then help our students actually be able to do this, and therefore approximate the work of scientists and engineers. If I change that shape slightly differently, this is like the icon for the next generation science standards, where the blue are the science and engineering practices, the green are the cross-cutting concepts, and the orange are the disciplinary core ideas. And if I think about this, thinking about from the approach of the scientist or the student working as the scientist and sparking curiosity, these are the things that we do, that we think and link actually, and then we come to know. And so we have our students really work in the blue and green space to come to generate knowledge that we hope they get in that orange space, but also we leverage the ideas that students bring to them in the classroom. They already have knowledge. They are not empty vessels. And so how do we build from where students are and help support them and move them to thinking that becomes more sophisticated and scientifically aligned? So I'm going to pause for just a moment and let you process, and you could reflect in a notebook if you have one, or on a sticky note, or if you'd like to reflect in the chat, we welcome you to do that. And just take a moment, I'll just pause for a minute or two to have you think about what you might see or hear in a classroom if students are experiencing three-dimensional learning. And when that learning is centered on them explaining phenomena and solving problems. So like I said, I'll just pause for a moment or two, and you're welcome to do that in the chat or in your personal notes. And we'll pick up in a moment. Give you about 30 more seconds. All right, thanks for taking a moment to pause and reflect. And I love the comments that are popping into the chat. And I think I would agree with my own observations of the excitement and the engagement that happened in the classroom. And Hillary, your point about uncertainty is really important. So in a little while, we'll get a little snippet from a classroom, and maybe we'll see how a teacher supports students with some of that uncertainty. It's always really great to see that. So what we're going to do is consider how these innovations and in the three dimensions and making sense of phenomena and problems apply to a classroom that has started to implement the NGSS. And we're going to continue on our first grade sound story. So we're going to pop back into thinking about that, but unpacking some of the practices that are at play that support student sense making. And so we're going to go back to that first grade example. And I just have a couple still photos for you for this one, where first graders actually are really thinking about a fire truck as a phenomena to consider, and thinking about that it's incredibly loud. And that's pretty exciting. And we can all agree that it's really loud. And students eventually share some of their noticings and some of their wonderings about fire trucks. And eventually in those, we can get a sense that we think that something's going on with the fire truck communicating in some way. Like, why is there a siren and why is it so loud? And so students have the opportunity to share those observations and those wonderings. And they also consider related phenomena. So what other things are using sound to communicate? And this leads them to really think about some objects in their classroom that also make sound and might be communicating with sound. And students really come up with some investigations that they can do to understand a little bit more. And they're offered the opportunity to investigate with some homemade instruments. So in this case, you're seeing a student hold her notebook. They were using spoons to actually make sound. And they had the opportunity to build a box drum. So just a box with some rubber bands, not a drum, but a guitar, to see what's going on with the sound. And they, through their investigations, they are observing patterns and start to have conversations around cause and effect. And here you see in the notebook, the students were asked to explain how an instrument they were working with was making sound. And so this one student wrote, the spoon, if you drop the spoon, it will make the sound. And from that, we started to ask other questions about what is causing that sound. And so the next move in that particular sequence is to have students move their thinking onto a chart paper. And that ends up being a really important thing because it turns out that we need to make our thinking public in science, because it turns out that science as a human endeavor is a public thing, and we negotiate and socially negotiate our ideas with each other all the time. But since we're first graders, we're going to take our own little corner of the chart paper. And as we put our ideas on the chart paper, we are having conversations about what's going on with the sound, and the teacher is facilitating some of that conversation. And what's really wonderful is one of the takeaways from the teacher who did this activity, where she noted that we finished the next 3 instruments and shared in a group, and the kids were saying, it feels bumpy when you touch it. I can hear the bumpy, I can feel the bumpy. And I asked questions to get them to the vocabulary word vibration. So it was really through her questioning that the kids translated bumpy into vibration and started to apply that academic language to their exploration and what they were doing. So the teacher ahas, I think I noticed you commenting that there'd be a lot of student ahas, and there usually are a lot of teacher ahas with this as well, because when we experience these innovations of centering instruction in phenomena and in the 3 dimensions, students are building their knowledge through the practices, just like scientists do. And in this case, you saw in the previous example, through investigation and through modeling, and experiencing that with students tends to be really transformative. And so I have a couple quotes from some teachers reflecting on this activity, and you'll note that their takeaways are really profound. So students can do this. Be patient with the time that's needed. It does take time to help students move their ideas. Students are willing to learn through struggle. So even though it might be a little tricky and we might disagree on things, we're willing to persist with that because we're really interested in what's going on and we want to come to know. And I think this one is the most profound for me, but really recognizing that students have more than we thought they did. And so the science and engineering practices then support students in constructing new knowledge and negotiating their understandings and how we come to understand and build that new science knowledge. And so they're really important for that. And I do want to reinforce one of the points I made subtly before, and that's the idea that science gives us a gift of these science and engineering practices. And so that means that students have the opportunity to play in the space of investigation, of modeling, of working with data, et cetera, to be able to come to know and to make sense of things. And it gives us the opportunity for us to let that happen in their everyday language. And once we understand that students are building understanding of a concept, then we can go and help support them and reinforce them by supporting academic language. And so it's that really subtle thing where the bumpy becomes the vibration, but the vibration now means a lot to kids because they got to work through their ideas first, and will probably forever associate it with bumpy, and that's okay. So with that, then what we want to do is kind of think about what this type of learning looks like. And this time I'm going to take you to a different project. This is a national project, Open SciEd, and it's aimed at creating free, high quality instructional materials aligned to the standards, as well as professional learning opportunities for educators, with the goal of being free to the public. So anybody can access very high quality instructional materials. And it goes through quite a rigorous development process. And we are proud to be the representative for California on the steering committee for Open SciEd, where we have a role in influencing development, but we also run a field test for Open SciEd in California. We've done this for middle school and high school, and I'm super excited. We're now on elementary, and these are our last batch of teachers that we just worked with to start field testing their units this fall, or this spring rather. And what I'm going to do is share with you a journey from what they're going to be testing for first grade this coming spring. And just because I am sure we're going to get asked the questions, these units will eventually be publicly available after the field test. And what happens is we take all the input from teachers and their students to improve the materials. So we make sure that they work in all kinds of classrooms. So the very first units of Open Science Elementary will start to be released in the end of August. And then it's probably 6 to 8 months time frame before we start to see the remainder come out. So we're going to see a sneak peek from this. So nobody else has seen this but field test teachers. So I'm going to share a little snippet of what's happening in a first grade classroom. And I do want to just provide some guidelines for the context of watching videos. These are real classrooms, or this is a real classroom, I should say. It's not staged. And just know that we don't know everything about the context. We don't know anything about the relationship between the teachers and the students, or even much of what happened prior to us popping in to see the video. And so as we watch, please presume positive intent and expertise on the part of teacher and kids. Assume that what kids say makes sense to them, and focus on what the teacher and students are doing to support equitable sense making. So I'm going to give you a little context first so you do know where we're dropping in. And in this case, in this particular sound unit, rather than a fire truck, students are considering a bell tower that uses sound to communicate. So a similar parallel. And we're dropping in on their third lesson where students are investigating instruments that make small movements when we hear them make sound. And they are the ones planning and conducting an investigation. They are the ones using a lens of cause and effect to make sense of that, and ultimately coming to the understanding that sound makes matter vibrate, and vibrating matter can make sound. And I could show you the investigation, but I actually think what's much more profound is to see what happens after the investigation. And so that's the part that I'm going to share with you. So just prior to this, the class was working with objects. And very similar to the previous example I gave you, they had a box guitar. They also had spoons, and they had a drum, and they had a shaker can. And what was interesting is when students were working with these, they're confused about what's making sound. So in the shaker can, they can actually see that there's balls moving, but they don't know if they feel any movement. So they're not sure if the can is moving. However, if they look at guitar strings, they see guitar strings move. So they're a little perplexed at what's going on. And this is where we drop in. So as we watch, think about how students are using their science ideas to make sense of the phenomenon. Maybe think about how the teacher is helping the students engage with the 3 dimensions through the questions that he's asking and how he's probing them, and what features do we see in terms of like offering classroom support for equitable sense making. Oh, and I will say, because this is a sneak peek, I don't have closed captioning on this. So you might want to turn up your volume. The kids are a little hard to hear. However, the teacher will repeat it. But I also can suggest that I think you're able to enable closed captioning in Zoom if that helps as well. But he will be repeating back a lot of what students say.
So what about the drum? What part is moving when the drum is making a sound? What do you think? The stick is moving? What do you think? Okay. You agree? How many people agree that the stick is the thing that's moving when it's making the sound? Okay. What is the stick hitting? The drum. Okay. Do we think maybe any part of the drum moves? No. You do. What do you think? Say more about what you mean by pulling it back.
Like it goes a little bit back. Wait. Show us the bottom and hit it.
Show you the bottom and hit it. Okay.
Yeah.
It moves.
It does move.
So. Oh, that's interesting. Put your finger on that. Put your finger on that. Go ahead. Watch what happens when I hit it. Do you feel it?
Can I feel it?
Do you think it moved then if you felt it?
Yeah, but you don't see it move.
Oh, okay. So I like what you're saying. Good.
I see, but you don't see it move. If you put more than one finger on it, it won't make the thing sound.
Oh, that's interesting. Okay, cool. Let go. Okay, go back to your seat. Okay, so wait. So I think we realized some interesting things here. I like what you're saying about that maybe we can't see it, but maybe we do know it's moving, even though maybe we can't see it. What about the spoon? Did the spoon have a part of it move? What do you think?
The spoons when you're like, and then the other spoon, and then the other spoon goes like down. Goes like down.
Okay, okay. So you're saying the spoon goes down a little bit and that makes it like rattle or shake. Okay, okay. I saw your hand up. Did you want to say something about the spoon? No, okay. Okay. I saw another hand up. Somebody else had a hand up about the spoon. You wanted to say something? No? Okay. Water? Yeah. Okay. So it seems like every one of these has a part that moves. Do we agree with that? Do we agree that every single one of these has a part that moves? Yeah? Do I have everybody? I don't have everybody. Who disagrees?
With what?
Tell me more. Is there one that you didn't see move? Yeah, which one? The drum, you didn't see it move?
It goes a little bit back. It's because you can't see it as well.
Oh, okay.
You can't see it.
Yeah. Okay. So we could feel it, but maybe we couldn't see it move. Yeah?
We could see it a little.
Okay.
No?
Ooh, okay, this is interesting. So we have a little bit of disagreement about maybe what's happening with the top of the drum, right?
You can feel if you can see it. No?
Say that again.
Like, feel all you like, you can feel all it can feel.
Uh-huh.
We can see it and we can feel it.
Both
I know,
of them.
but you shouldn't circle it because you can only feel it.
Oh.
And that one says feel.
Okay. So some of us
Circle that one, not that one.
some of us saw it, some of us maybe didn't, right? So I have this interesting book that I think could help us find out a little bit more about what's happening when things make sounds. And right now I hear lots of sounds with our papers, right? So like, how does that work? Maybe we could find out some stuff about that. So let's put our papers down out of our hands so they don't make any more sounds while we check out this book, okay?
Did you notice the girl making the periscope so she could see the drum better? All right, so we're gonna stop the video here, but know that they get to read that book.
So what about the drum?
There we go. They get to read that book and they start to negotiate their ideas. And the class goes back to this initial model that they created together. It's a class consensus model. And they apply some of their new thinking from the investigation and from the book onto the model to modify their thinking about where they are now. So I'm going to pause one more time and invite you to take a moment to put some ideas in the chat from what you noticed happening, how students might be using their science ideas in conjunction with support from the 3 dimensions and working with the phenomena, and how the teacher's helping the students engage with those dimensions, and how we're supporting equitable sense making. And Farida, I see your question in the chat. The book is being created for Open SciEd. So when these materials are publicly released, those materials will be released as well. So I'll give you a moment to chat some ideas, and we'll move us on into our last couple minutes. All right, so usually there's a lag time with typing, and so I apologize. I'm going to move on because I'm watching the clock, and my fumble at the beginning didn't help. And so thank you for continuing your thought and sharing that with each other. It's nice to see how people are processing. One of the things I did want to surface is that one of the focal areas of professional learning that's really needed to support this type of high quality instruction in our classrooms is supporting teachers with discourse. So if we are supporting students with their thinking, their sense making, we're also supporting them in socially negotiating those ideas and discussions, whether it's between a student, myself, or in small groups of students, or even with a whole class. And again, that's just really critical because that's how we start to really strengthen our sense making. And we do this in collaboration with others. So I did want to share, this is one thing I can share with you, is that a draft resource to anchor this type of work really is now available from OpenSciEd. The teacher handbook that's in draft form is available. And in it, you're going to find some guidance on supporting sense-making discussions with students. And what'll be really exciting is later when the lessons are released to the public, we will find these shaped in context with the particular lesson that teachers are engaging in to help support that discussion that was happening. But I also just want to surface like the brilliance of teachers, because, you know, when my whole class is all making sounds with paper, I love seeing that he just went with it and supported the students with that and played with that idea that their papers were also making sound. And no instructional material probably is going to predict that. So it's pretty exciting to see wonderful teachers in action. So the last brief reflection that I'd like to ask you to do is to think about how this might be similar or different to your own experiences in science. So for you as a learner, or you as a teacher, or somebody who observes teaching. And so take a moment to kind of hold on to that and think about what might be different and what other questions you might have for other learning that you can engage in. That's always something that's great to communicate back to our folks who hosted this meeting, because we are looking to expand our resources to support, you know, not just math, but math, science, and computer science in our classrooms. And the other summary that I just want to make is this really important punchline that what we're hoping to see more of in classrooms is not necessarily how I learned science when I was a young kid, but instead we're hoping to see learning and use in context, seeing how our learning applies to the world around us, and taps into those curiosities that we have about the world around us, and that we get support in moving our thinking. We already have thoughts about the world. So how do we move those to be ones that are more scientifically aligned? And that happens over time. And so it's just not the teacher that's the knower in the room, but the students know that they are the knowers in the room, and they have the confidence in that as well. And so with that, hopefully we support curiosity and sense making in our students. I'm going to skip this because I don't think we have time, but I'll leave this up. So if you'd like to get in touch with us, you're welcome to email Andrea or myself or the folks that hosted the meeting. And I think we have just a couple seconds left that I'll go back through and monitor the chat in case there's been a question. But I don't want to forget to mention that you'll want to pop back over to the main session. So you'll want to enter the lobby to do so. And that will connect you back into the closing. And so with that, I thank you all for your time this evening. I wish I could have seen your faces. It's a little weird not to do that, but we're grateful that you took the time to be here. Whether or not you already know some about NGSS or this is new, we're excited to move forward together. So thank you. Yeah, we're all looking forward to seeing the end of the production of the books. It's been fun to see them. Thanks, everybody. Have a great evening.